Thank you. So I am going to talk about a paper that I did during my PhD with my advisor, Dr. Jinglai Shen at UMBC. Uh, which is basically about uniqueness of the solutions of convex piecewise affine functions. And then we apply them, if we have time, to L1 minimizations. So I'm going to talk about compressive sensing to motivate the problem. And if these things are introductory, I am sorry, but I will be fast. So sparsity is like for a vector, most of the components to be zero, and a sparsity level is number of non-zero elements. Sparsity itself is a hard, like very strict constraint, and actually you don't have numerically, like in practice, things are not exactly zero, so we go for compressibility, and that basically means you can approximate your sparse signals, your vector with a sparse signals. For example, you can say 1, 0, 0, 10 to the negative 8 can be approximated by a sparse vector. So that's a compressible vector for us. So what is compressive sensing? Now we can assume that, so basically we can assume that without loss of generality, every vector that we have is sparse, because if not, people have observed that using sparsifying basis, you can actually like multiply your vector by a matrix and the result is sparse. This is something that people have observed in practice. So without loss of generality, we can assume that the vector of desire is sparse vector. And now we want to use the structure of this this sparse vector. So instead of sending this long, we can you can assume that the length of this vector is very long, Rn, and capital N is very large here. So instead of sending this x, you want to send this y, which is AX. So it's a measurement using this design matrix or measurement matrix A, and send y to the receiver, where M is basically much smaller than capital N, which we said is a big number. So a receiver, if we introduce norm 0 of x as cardinality or number of non-zero elements, has this knowledge that your vector is sparse. So how is going to model the problem? Naturally, because you know y is equal to ax, you have this constraint, and because you know it's a sparse, you go for the sparsest solution of this underdetermined linear system. So this problem is the original compressive sensing problem, and it has lots of applications in, for example, signal processing, image processing, but it is NP hard. So what are the three? There are three different, three categories of algorithms in compressive sensing to tackle the original problem of compressive sensing. The first type are going to be a sparsity-based optimization algorithms. So we know LP goes to L0 as P goes down to 0. Therefore, we can approximate that original problem by replacing norm 0 by norm P. We know that norm 0 is not nice. I mean, it is non-convex and it is discontinuous. So it basically has some difficulties. And then by replacing norm P, you can kind of escape from some of the hardships. And the greedy algorithm, they directly tackle this problem and they say, what do I want after all? I want the sparsest solution of an underdetermined system. So why not start from 0 and then add only one index, which is locally good, and then go for basically after you update your support set, you do a projection step. And under some conditions on A, you can show that such algorithms are also convergent. And there is another category, thresholding-based algorithms. So their idea is they use this A transpose somehow like A inverse. So if we knew A was like orthogonal, A transpose was the inverse, but there is no A here is not square. So, but they use A transpose like A inverse operator here somehow, and then use this hard thresholding operator, which only keeps, for example, S largest components of whatever vector you have inside in absolute value. And basically they are using fixed point methods. Now, what are the main problems in sparse optimization? This is a generalized basis pursuit when you have P, any P bigger than or equal to 0. And then here you have like noisy case, and here people are like kind of replace objective and constraint. And ridge regression for P equal to 1, we know it's LASSO, and here again for P and R equal to 1, for elastic net you have the standard elastic net. So what does it?
Excuse me, could I ask a quick question before you go on?
Sure.
So on your previous slide, the algorithms that you mentioned, so are they, you mean these are in general used for sparse problems, or for the original compressive sensitive problem, or for the one where you replace the L0 norm with the LP norm?
So in the first category, they can actually use for, here. Yes, we have, so if you have P equal to 0, as far as I know, there are at least greedy algorithms for these two, I am sure. For the first category, when P is equal to 1, when you can like approximate norm 0 with norm 1, there are results for all these cases. And for the thresholding based, I know that they are tackling these two at least. So it's not necessarily, because most people go for noisy case sometimes. So it's not necessarily for the original problem. They also work on these problems as well, if that answers your question.
Yes, thank you.
Oh, okay. So here's a geometry of what happens when you have different P's. As you can see, this is like y equal to ax in the left side. And then these are the unit balls for different LP norms, and P between 0 and 1. You have this this non-convex unit ball here inside that diamond shape. And as you can see, where y equal to ax touches that unit ball happens to be on the x-axis, and that basically is a sparse point for us on R2. And for P equal to 1, also this case happens, and you have a sparse vector. For P is strictly bigger than 1, you can see that here is where we touch that unit ball, and it's not, you have two non-zero components, so the solution is not a sparse. And here is the geometry when you have the second, this case here, and you can assume that A is generically, this gives you an ellipsoid that feasible sets, and the same geometry goes on. So P equal to 1 is a good choice, and it actually results in a convex program, but it has some issues. And what is the issue is that you do not have necessarily a unique solution. P between 0 and 1 is non-convex, so people actually recently people are going through that, and P bigger than 1 doesn't give you good results. And actually we could show with Dr. Shen that not only you do, basically all the components are going to be non-zero except from a measure 0 set. But my focus here today is on norm 1. So these are the problems that people use in norm 1. As I said, you can actually capture sparse solutions, but the problem is that you do not have necessarily a unique solution. And some of the engineers basically, whenever they face with a norm 0 problem, they replace norm 0 with norm 1, and then they recover a solution. Now the first question is that whether this solution is unique or not. So, so the problem comes from that norm 1 is not strictly convex. And if that is not the case, if the solution is not unique here, basically based on the language recovery process is not successful, because you don't know this is what you wanted or not. So there are some literature review here, and people have worked on, for example, basis pursuit and basis pursuit denoising type 1 here. And for example, you give A the problem parameters, and they can tell you that the solution, the given solution is unique or not. And there are some later people in 2012, I guess, people worked on when you replace norm 1 with norm 1 of EX. And then 2016, I guess, Gilbert replaced norm 1 with a polyhedral gauge. And Dr. Zhao in, I think, Liverpool, he established necessary and sufficient conditions for non-negative sparse vectors. So he actually has extra conditions here that X is also bigger than equal to 0. So we said, can we improve these results? And we actually motivated by these problems, for example, minimization of norm 1 subject to these constraints. As you can see that this is Danzig selector, and these constraints can be written as Cx bigger than equal to D for some matrix C and vector D. So this is a polyhedral constraint. So it motivated us to have polyhedral constraints included in our formulations, and we can go beyond norm 1 and norm 1 of EX. For example, in fused LASSO, you have such a objective function, and we wanted to come up with some general classes that include these types of problems as well. And we wanted to have conditions, the solution uniqueness conditions, that they are actually computationally favorable. So that's why we added general constraints, and we consider convex piecewise affine functions that actually includes these such objective functions. And also we used a unifying approach that I will explain shortly. So these are the problems that we have considered. These are generalization of what I introduced before. And here, so imagine A is a measurement matrix and C is some kind of polyhedral constraint matrix. And then F is is a C1 strictly convex. In practice, people only, usually consider norm 2 squared. And also G of X is a convex piecewise affine function. And surely you know that G of X, like for example, a special case is norm 1. So we consider these cases. These problems are actually convex because of the assumptions that I just made. So how we approach to tackle these problems? I have 7 minutes, I guess, if I am, or I do not have time. Do I have time? Okay, so a convex piecewise affine function can be written in this way. There is a proof for this. You can write every convex PA function as this. And now imagine that I am given X star in Rn, and I want to know whether this X star, which is feasible for one of these, for example, we focus on this one, for basis pursuit-like problem, is it the unique solution of this problem or not? And so I need to define this alpha set, which is basically active constraints, and I, this script I, which are the active affine functions at that point X star. So I can define this W. You can actually show this W is related to convex Hall generators of subdifferential of G of X star. So we understood that our results basically reduced to this question. I give you two matrices A and H, under which conditions on these two matrices I can basically say that this set is a singleton of 0. And we found out these two conditions are I and double I. So because of lack of time, I don't go through the proof, but you can see in the next slide what happens and how the question reduces to these two conditions. So here is the main slide of my presentation. So imagine, assume X star is feasible point of the optimization problem basis pursuit-like problem to make sure that you get this one. So you have AX equal to Y, CX bigger than equal to D, and G of X is a convex PA function, which, as I said, has this max formulation. You can prove that. So now I want to know if X star is a unique minimizer of this problem or not. So the idea is, because my problem is convex, if I want to have X star to be globally unique, I have to have this X star being locally unique. So now that it has to be locally unique, I can basically perturb X star. And so for sufficiently a small norm of V, you can show that this relation holds. And now X star is unique in its neighborhood for sufficiently small V if and only if I cannot move along any direction and basically improve my objective function. And that basically means 0 is the unique solution of this problem. And because AX star is equal to Y, so A of V becomes 0, AV becomes 0, and you can see that only I care about active constraints here. And using that relation here, I can have this. And now the third thing is to notice that 0 is the unique solution of this problem here, if and only if this situation happens. And maximization of PI transpose V is less than equal to 0, which actually is equivalent to WV less than equal to 0. So you can see that for some matrices A and H, my problem reduces to this question. Now I use these two results to come up with the conditions which are here. Next, this procedure can be used for all other problems, actually, with more obviously like technicalities. But the idea is the same, using that if the solution has to be globally unique, has to be locally unique, and some more analysis for other problems. And the next thing is how do we basically check these constraints? You can see that this one is basically linear independence, so it can be done easily. This guy here is the problem which you have strictly strict inequalities. For that, people used in literature suggested like barrier algorithms, but for us, we noticed that eventually what we want to check the feasibility of is this system AX equal to Y, and then are there a positive, and this is component wise. You can actually show that this system has a solution if and only if this linear program finds a positive optimal value. So what does that mean? Instead of using those logarithmic barrier functions that people use in practice in the literature to check the feasibility of such system, you can actually use linear programming. So so the message is we work with convex piecewise affine functions, and we can actually come up with linear conditions that you can check them with linear programs, and the other things also can be used by linear program or linear algebra. So everything reduces to linear algebra linearly after all. And here are some references, and thank you for your attention. Sorry if I took a lot of time.